This is our last section in Unit 5. It's a good summary of what we've learned over the last 3 or 4 days dealing with enthalpy and entropy. So if we remember correctly that in terms of enthalpy, delta H, we know that an exothermic reactions, remember when delta H is a negative value, they're more likely to occur. And the way that we say that is we say that they're more thermodynamically favorable. That doesn't mean they're going to occur. It just means that in comparing an exothermic reaction with an endothermic reaction, the exothermic reaction, the one with the negative delta H, is more likely to be thermodynamically favorable than, again, an endothermic reaction is. And then in terms of entropy, we can actually apply entropy. Remember, delta S is a measure of disorder. That same concept can be applied. That reactions that become more disordered, which again have a positive delta S, are again typically more thermodynamically favorable than reactions that have a negative delta S that are becoming more ordered. Now what we can do is we can take both of those concepts and we can put them together. And by that I mean if you have a negative delta H, which again we say tends to be more thermodynamically favorable, and we have delta S with a positive delta S that again tends to be more thermodynamically favorable, then the reaction is going to happen. And by going to happen, we mean that it is always going to be thermodynamically favorable. Okay, but then the opposite also occurs. So if a reaction, if it is exothermic and it becomes more disordered, so if delta H is negative and delta S is positive, again, it's always going to be thermodynamically favorable. So the reaction will always spontaneously proceed in the forward direction. Okay, then the opposite also occurs if it's endothermic, so delta H is a positive value, and it becomes more ordered, again, you've got your negative delta S there, the process is never thermodynamically favorable. Okay, now what we can do is mathematically, let's combine all of these things together, okay? And when we combine all of these things together, we get this new term that is called delta G. And delta G, the G stands for what we call Gibbs free energy. So the Gibbs free energy is a measure of whether the reaction is thermodynamically favorable or not. That's what delta G tells you. Delta G is absolutely, is this reaction going to be thermodynamically favorable or is it not? Okay, and what it does is it's all based on obviously the enthalpy change, the entropy change, and then obviously the temperature. Now the temperature, just like with gases, must be in Kelvin. It's not the temperature change, so it doesn't necessarily, you can't have it in Celsius. It does have to be in Kelvin every time. Okay, and we said up here, we had said that when delta H is negative and delta S is positive, well, if delta S is positive, we know this whole thing here is therefore negative. So you're taking a negative number and you're subtracting even more, so therefore delta G is negative. So when delta G is negative, the reaction is always thermodynamically favorable. That's what tells you. Remember we said, if it's exothermic, it tends to be thermodynamically favorable. Well, now we can say with a surety, 100%, if delta G is negative, then the reaction absolutely 100% of the time is thermodynamically favorable. Okay, and it will proceed spontaneously in that forward direction to the right. Okay, and the opposite also is true. If delta G is positive, so think about mathematically what happens here. If delta H is positive and delta S is negative, then again, this whole quantity here, a negative and a negative, makes it positive. So you've got a positive number and you're adding another positive number to it. Again, that's what happens here. Then again, delta G 100% of the time is going to be positive, and again, it's not thermodynamically favorable in that forward direction. Okay, so like we said earlier, when enthalpy is negative and entropy is positive, the Gibbs free energy will always be a negative value, meaning that it is thermodynamically favorable. Okay, a thermodynamically favored reaction may still be slow. This says nothing about speed, especially if the activation energy is high. So a reaction that has a negative value for delta G may not necessarily occur at a measurable rate. So it might not be quick, but it is still going to occur. When a reaction is thermodynamically favored, again, lots of products will form, and this we're going to learn about this in the next unit. K, the equilibrium constant, will be greater than 1. Again, we'll get to that later on. Okay. However, when the enthalpy is positive and the entropy is negative, again, the Gibbs free energy will always be positive, and that results in a thermodynamically unfavorable reaction. Okay. So this equation up here is really, really helpful for basically trying to figure out, is this reaction thermodynamically favorable or not? And again, if delta H is negative and delta S is positive, it's always thermodynamically favorable. It's exothermic and it's becoming more disordered. Okay, absolutely. That's a negative delta G every time. And when it's endothermic and it becomes more ordered, then again, delta G is always going to be positive, and it's never thermodynamically favorable. Okay, we talked about this in class, I believe, yesterday, but one of the things that we need to remember is that entropy, the units for entropy, are almost exclusively given. Usually it's joules over Kelvin mole. And the Kelvin is there because then the Kelvin there and the Kelvin in the temperature will cancel each other out. The problem is delta H enthalpy values and delta G are typically given in kilojoules. So one of the things that you're going to have to do is you're going to have to convert your joules in the entropy component to kilojoules. So it's very important that a conversion from one unit to another match each other. Gibbs free energy, again, is typically measured in kilojoules per mole. So the entropy needs to be converted to kilojoules by dividing by 1,000. Okay, obviously if the units don't match, then your answer will be incorrect. Okay, now we've looked at two examples so far. We've said when the enthalpy is negative and the entropy is positive, delta G is always negative and it's always thermodynamically favorable. Okay, but then the other side, if it's endothermic, delta H is positive and delta S is negative, then delta G is always positive. So one thing that I always think of is if the signs are opposite of each other, by that I mean delta H positive, delta S negative, or vice versa. If delta H is negative and delta S is positive, it's either always thermodynamically favorable or never thermodynamically favorable, depending on which ones are positive or negative. But then the question arises, what happens when the enthalpy and entropy are both the same sign? Like I said, so far the two examples we've seen, their signs have been opposite. One's been positive, one's been negative, and vice versa. But what if it's exothermic, delta H is negative, and it becomes more ordered? Delta S is negative. Or what if they're both positive? What if it's an endothermic reaction that also becomes more disordered and delta S is positive? Okay, so then you can't say always thermodynamically favorable or never. Okay, there's one more component of this equation. So if delta H is positive and delta S is positive, really it comes down to the temperature. Okay, because if the temperature is really, really low, then what has a bigger impact on delta G is the enthalpy. So at a really, really low temperature, not really low, but at a low temperature, we would say that what's driving this reaction is the enthalpy component, because the temperature is so low that this part of the equation isn't having much of an effect on the value of delta G. So at a low temperature, delta G is going to be positive and it's going to be thermodynamically unfavorable. Okay? But as the temperature goes up, so at a high temperature, now this component, the negative T delta S component, now plays a bigger factor, and then delta G at some point, depending on what the values are, is going to switch from being positive to being negative. So when they're both positive at low temperatures, the delta H component, again, at a low temperature, the delta H component has a bigger impact. It's what's driving the reaction forward. At a high temperature, though, the negative T delta S part of the equation is driving the reaction. And therefore, again, when delta S is positive, this whole thing is negative. So then delta G is going to be negative. Okay, this is all summarized here in this table. Okay, and again, I like to think about it, again, more of understanding it instead of memorizing some table. Okay, and these two here we've already talked about. This right here and this right here. When delta H is negative, exothermic, and delta S is positive, it's always thermodynamically favorable. Okay, and then when delta H is positive and delta S is negative, again, it's always a positive delta G. It's never thermodynamically favorable. It's when those signs are the same, when they're both positive or both negative. Again, it depends on the temperature. Again, at low temperatures, this is the one we were just talking about, at low temperatures, delta H has the bigger impact. So it's going to be a positive delta G. But because remember that the delta S is in that negative T delta S part of the equation, when the temperature gets high, when delta S is positive, again, this whole thing is negative, so that makes the delta G become negative. Okay, same thing down here on this one. Okay, when they're both negative at low temperatures, what drives the reaction forward? The delta H value. And so it's exothermic. Because it's exothermic, that's going to make delta G negative at low temperatures. But then as that temperature goes up, once you reach a high temperature, now that negative T delta S in here, that delta S is negative. And so a negative and a negative makes that whole quantity here positive. So as the temperature goes up, it's going to switch and it's going to not be thermodynamically favorable. Okay? So that's going to take some practice. That might be a good thing to review. Maybe back up the video just a few minutes and watch that part again, because this information right here is really, really important. And again, I wouldn't memorize that. I would just, if you know delta G equals delta H minus T delta S, which is, by the way, given on the AP exam, that again, just put in a negative and a positive here and go, well, if that's negative and that's positive, then this is negative. Oh, delta G always has to be negative. Okay, and when the signs are the same, though, that's when you really got that temperature component. Well, what is actually a low temperature? What's a high temperature? There is no low temperature versus high. They'll just say low temperature versus high temperature or something like that. Okay, let's look at an example problem dealing with this. It says the following reaction occurs at 25 degrees. There it is. Delta H is negative 315. Delta S is negative 1250. Is the sign of the entropy logical based on the reaction? Well, the sign of the entropy is negative, and we're going from 3 gas particles to just 1 gas particle. So I would say absolutely yes, and explain, because again, you're going from 3 gas particles to just 1 gas particle. And again, 1 gas particle is much more ordered than 3 gas particles. Okay, next question. Is this reaction thermodynamically favorable at 25 degrees Celsius? Justify your answer with a calculation. Well, again, now we can know for sure. How do we calculate whether something is thermodynamically favorable? Using delta G. So delta G equals delta H minus T delta S. So delta G is going to equal delta H, negative 315 kilojoules per mole, minus the temperature, 25 degrees, change that to Kelvin, 298 Kelvin, times the delta S value, which again is in joules, so here's where we got to be careful. That's going to be negative 1.250 kilojoules. I move that decimal point 3 spaces to the left, over mole Kelvin. Okay, and now I need my calculator, so I'm going to take negative 315 minus, and then parentheses, 298 times negative 1.25, close the parentheses, and I get a delta G value of positive 57.5 kilojoules per mole. Okay, and simply all we would have to say is it's not thermodynamically favorable. And why not? Simply because delta G is a positive value. And that's your explanation on the AP exam. Okay, and then it says, all right, fine. If it's not thermodynamically favorable, okay, when does it become thermodynamically favorable? Well, we know when the delta G switches from being positive to negative, then it's going to become thermodynamically favorable. When it switches is when delta G is equal to 0. So we can take this same equation here, and we can set delta G equal to 0. So 0 equals delta H minus T delta S. And we can say, okay, they want to know the temperature. So to solve this, I'm going to add negative T delta S to the other side. That makes T delta S equals delta H. And then again, to get temperature by itself, I'm going to divide by delta S. So the temperature at which it becomes thermodynamically favorable is delta H over delta S. So delta H, again, is negative 315. And again, that's kilojoules per mole. Delta S is, where is it? Negative, and again, 1.25, got to be kilojoules. So negative 315 divided by negative 1.25 equals a temperature of 252 Kelvin is our final answer. Now, does that make sense? As the temperature goes down, because remember at 298, it wasn't thermodynamically favorable. But that temperature, as it drops, it becomes more thermodynamically. It's going to become thermodynamically favorable at 252. Let's look at our enthalpy value and entropy values. So because they're both negative, remember at a low temperature, what has the bigger impact? The enthalpy. Okay, at a higher temperature, what has the bigger impact? The delta S. So at 298, what's driving this reaction forward is the enthalpy. That's what's is the entropy. That's what's making this positive is the entropy component. Okay, once you hit 252 degrees now, or 252 Kelvin, now that temperature isn't having as much of an impact. So what's driving the reaction now? And I use that word a lot because I use it on the AP test. What's driving the reaction now is the enthalpy component. Okay, because the temperature is lower, which means that negative T delta S isn't having as much of an impact as it was before. So what's driving this reaction to be thermodynamically favorable at 252 is the enthalpy change. Okay, now just like before, just like with enthalpies of formation and just like absolute entropies, there's our last equation with delta G, that the Gibbs free energy for the reaction is equal to, again, the sum of the delta G of formation of the product. So there is a Gibbs free energy of formation, just like enthalpies of formation, minus the sum of the Gibbs free energy of formation of the reactant. So we've now got three equations, all look very, very similar, and they're all given on the AP exam. So this one is on the AP exam as well. And again, you solve it just the way you would with entropy, just the way you would with enthalpies of formation. Okay, if delta G is positive, we know it's not thermodynamically favored. The equilibrium constant is less than 1. Again, we'll get into that in Unit 6. And again, we can say that the reactants are favored, which means you have more reactants than you do products. Okay, and if it's 0, then the reaction is favored equally. So it's not really thermodynamically favorable in either direction. And again, we'll get into that more detail later on. Okay, how can you make this, not super important here, this is just the last little bit. How do you make a a non-thermodynamically favorable reaction occur? One, you can use electricity. Okay, you can break bonds. Water breaks apart into hydrogen and oxygen using electrolysis. We're going to learn about that in Unit 7. You can use light. Again, that's just another form of energy. you can put two equations together, one with a positive delta G and one with a negative delta G, put those two together, and then the one with, if the negative one is bigger, then overall it's going to be a negative delta G. Here's an example of that. This is positive, this is negative. Put the two together, and you get an overall delta G of negative 16.7. So kind of like Hess's law, where you add two equations together, you can add their delta G values together, and overall you get a new delta G. Okay, now one part that deals with, again, this is in this unit, that there is a mathematical relationship between the Gibbs free energy, and again, this K here is what we call the equilibrium constant. Again, we're going to see this a lot more in Unit 6, but we have seen how delta G can be influenced by temperature, but there's also, there's one more thing that we have to consider. Okay, again, delta G with that degree sign assumes that the standard conditions are 1 atmosphere and 1 molar for solutions. And that means that when the conditions are different from those standard values in terms of different pressures or different concentrations, that a previously positive or negative delta G value will take a new delta G value under these new conditions. Okay? In some cases, when delta G is pretty close to 0, not only does the magnitude change, but the sign changes as well. And so what that will do is it'll cause a previously non-favored reaction to become favorable and vice versa. Okay, there's an equation again that we're going to learn in Unit 6, but again, it's not even on the equation sheet. What you should understand is that initial conditions outside of standard one, so if it's not at 1 atmosphere, not at 1 molarity, may cause a favored reaction to produce very few products, and a non-favored one to actually produce some products. Again, we're going to talk about Q and K in much more detail in Unit 6. Okay, last thing, catalyst. We know a catalyst job when we learned in when we talked about reaction rates was to make the reaction go faster. Okay, we know it lowers the activation energy, it provides a different reaction mechanism, etc., etc. Okay, however, in dealing with delta G, it will cause the rate of the reaction to proceed faster, but it does not affect the thermodynamic favorability of a reaction. Okay, in other words, catalysts have no effect on the value of delta G. Yes, they make a reaction go faster, but no, they do not affect the value of delta G at all. That's the end of Unit 5.